Let's find out now a relation between electric field and electric potential. If any charged particle is experiencing a force in a region, we call it electric field. And we have done that electric field intensity is a quantity that is used to describe such a region. Now we will study about one more quantity which we call as electric potential. So electric potential and electric field intensity, or usually we call it electric field. So electric potential and electric field. These two quantities are used to describe a region wherever charged particles experience force. This is a vector quantity, this is a scalar quantity. First quantity, electric field, is related to force. It is related to work or energy. How do we find out the electric field intensity? We take a test charge, keep it in the electric field and see what is the direction of force. Force divided by this test charge, that gives us the field intensity. Same way, to find out the electric potential at a point, we put a charge, find out its electrostatic potential energy and divide it by the charge itself. That will give us the potential. So this is the force per unit charge, this is the electrostatic potential energy per unit charge. Now we want to see whether there is a relation between the two or not, and it should be. Work done depends on the force, and force decides the intensity. So let me take an example of electric field E. Maybe uniform, may not be, and this is the work done. If we are moving a charge in an electric field, a charge is moving in an electric field and the force is F, displacement dr, then the work done by the field is this. This is the force by the charge, by the field. If this is the field and Q is the charge, so QE is the force on this charge. This is how we calculate the work done by electric field. Okay. This is the work done by the electric field. Okay, if I need to calculate the work done by the external agent or the change in the potential energy, how do we write the change in potential energy? This is always equal to the work done by the external agent, not by the field. It is the work done by the external agent. And this is always the work done by the electric field with a minus sign. See, if the charge is moving itself in this direction, this is the work done by the field. If I apply a force in this direction so that this charge moves with constant velocity. So in moving it from one position to another position, work done by the field is say 10, work done by me, it is minus 10. Net work done is 0, and it should be, if the charge is moving with constant velocity, net force is 0 and the work done should be 0. So this is how. And how much is this? Minus QE dot dr. So this is the change in potential energy. And what is the change in potential energy? It is actually Q into the change in potential. So dV is minus E dot dr. This is the relation between the potential difference and the electric field. Now we can write it in. If I write E and R in terms of X, Y, Z component, then E can be written as EXI cap, EYJ cap and EZK cap. Same way, dr can be written as dx I cap, dy j cap dz k cap. And the dot product of these will be minus Ex dx minus Ey dy and minus Ez dz. This is the relation between electric field and potential in terms of xyz component. Otherwise, this is the general expression dV is equal to minus E dot dr. Now, if we move the charged particle from one position to another and the change is large, then we need to integrate it from R1 to R2 E dot dr. This is how we can calculate the potential difference between the 2 points. Now, we have already done that conceptually, but let us see mathematically also that if a charge is moving in the direction of the electric field, we always say that a charge left to itself will always move from high to low energy. So it also means from high to low potential. So it means if I take 2 points in the electric field A and B and this charge is moving like this, then the potential of A point is higher than the potential at B point. So electric field actually points in the direction of decreasing potential, or potential decreases in the direction of electric field. And this is quite evident even from this point. dV is equal to minus E dot dr. Now I can simplify and take two specific examples to understand it. If this is the field and the charged particle is moving like this, so theta is 0 in this case and dV is minus E dr. So E is minus dV by dr. Electric field is also defined as potential gradient. Rate of change of potential with distance is the electric field. Potential gradient is electric field. And electric field points in the direction of decreasing potential. dV by dr minus is electric field. Potential is a scalar, but potential gradient is a vector. dV by dr is a vector quantity. E is vector quantity. Potential is a scalar, potential gradient is vector. Electric field points in the direction of decreasing potential. Okay, this I have taken if they are parallel. What if I am moving the charge like this at an angle theta? Then this will be EV minus E dr cos theta, or dV by dr is equal to minus E cos theta. Then dV by dr will be negative of the component of the electric field along the direction in which we are moving. If we are taking in this direction, we have to take the electric field component in this direction. So dV by dr is equal to E minus E. If the charge is moving along the field, if charge is moving at some angle to the field, then the component of electric field in the direction in which the charge is moving is equal to the potential gradient. So that's all how we can find a relation between electric field and potential. Field means it's related to force, potential related to potential energy, and then we can find a relation between work done and the force, and hence between the potential and the field. Work done is force into distance. So the potential will be electric field into distance, because both are taken for unit charge. Potential and electric field, they are related by this expression. Negative of potential gradient equals the electric field. So that's all about the relation between field and potential. Bye.